Winds of change on the open sea. Imagine wind turbines the size of skyscrapers, not rooted to the seabed, but floating. Far out in the ocean, where winds blow stronger and steadier, these giants generate clean energy without disturbing marine ecosystems or competing with coastal land use. This is the promise of floating wind turbines, a new frontier in renewable power. Unlike conventional offshore turbines fixed to the seafloor, these structures are anchored by cables and buoyant platforms able to operate in water depths of hundreds of meters. And while it sounds futuristic, it's already happening. Prototypes and pilot farms are operational. The race is on to scale. Floating turbines could tap into vast, untapped energy reserves, quietly rewriting how we power cities, industries, and the global grid. Before we proceed to the video, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Why floating wind turbines? Matter, tapping, deeper waters. Most of Earth's strongest and most consistent winds lie offshore, in waters too deep for fixed-bottom turbines. Traditional systems max out at around 60 meters depth. Floating turbines, however, can operate in waters 400 meters deep or more, accessing sites previously off-limits. This opens massive potential off coasts like California, Japan, Norway, and South Korea, where wind is abundant, but the seafloor drops steeply. According to the IEA, over 80% of offshore wind potential lies in deep waters, precisely where floating turbines thrive. Minimal footprint, maximum impact. Floating platforms are towed into place. No pile driving, dredging, or seabed disruption. That means reduced impact on marine life, easier relocation or decommissioning, lower visual intrusion from shore, and because they sit far offshore, they avoid public opposition often faced by land-based or nearshore turbines. Complement to solar and land wind. Floating wind is intermittent but predictable, filling in the clean energy puzzle. At night or in cloudy regions where solar lags, floating turbines offer steady generation, especially useful for grid balancing and baseload support in renewables-heavy regions. How it works. Ocean engineering meets wind power. Buoyant foundations. There are three main types of floating turbine platforms. Spar buoy, a tall, weighted cylinder below the waterline. Extremely stable but requires deep waters and specialized towing. Semi-submersible, wide platforms with multiple columns, partially submerged and balanced by ballast, easier to tow and deploy. Tension leg platform, anchored with taut cables to the seabed. Compact and stable, but demanding to install. Each is chosen based on water depth, wave conditions, and installation logistics. Mooring systems and anchors. Cables connect the floating turbine to anchors on the seafloor. These lines, usually a mix of steel chains and synthetic ropes, keep the platform in position but allow natural movement from waves and wind. Advanced modeling ensures that mooring systems hold firm without overstressing the turbine. Flexible power cables. Electricity generated by the turbine travels through dynamic subsea cables designed to flex with the motion of the platform. These cables connect to a collector hub and then to the onshore grid, often via subsea substations. Real-time stabilization. Onboard sensors and smart control systems constantly adjust blade pitch, yaw orientation, and ballast levels to stabilize the turbine. Combined with aerodynamic tuning, these mechanisms prevent structural overload and optimize power output, even in rough seas. Real-world projects and momentum. Hywind Scotland, the world's first floating wind farm, Hywind Scotland, launched in 2017 with 6 megawatt turbines on spar buoy foundations. Despite harsh North Sea conditions, it has consistently outperformed fixed offshore wind farms in capacity factor, reaching over 50%. Wind Float Atlantic. Off the coast of Portugal, WindFloat Atlantic uses semi-submersible platforms to host 8.4 megawatt turbines. It marked the first time such large turbines were deployed on a floating structure and towed into deep water without cranes or ships. California and Asia-Pacific expansion. The U.S. West Coast, with deep Pacific waters, plans multiple floating wind auctions in the coming years. Japan and South Korea are aggressively piloting similar projects, seeking both energy security and decarbonization. In total, over 150 gigawatts of floating wind capacity is in planning or early development globally. Challenges. Still on the horizon. Cost and scale. Currently, floating turbines cost 30 to 50% more per megawatt than fixed-bottom offshore wind. This is due to complex foundation design, mooring and anchoring logistics, expensive dynamic cables, port and towing requirements. However, as floating systems scale and supply chains mature, costs are expected to drop by over 60% by 2030, making them competitive with fixed offshore wind. Harsh ocean conditions. Floating platforms must survive extreme wind, wave, and saltwater corrosion over 25 to 30-year lifespans. Designing turbines to endure these forces without excessive maintenance is a major engineering hurdle. Structural health monitoring, self-healing materials, and autonomous repair drones are in active development to mitigate this. Grid integration. Bringing power ashore from distant offshore sites involves high-voltage subsea cable routing, grid upgrades at landfall points, balancing transmission losses. Some developers are exploring offshore substations or even floating energy storage to buffer output. The future, floating farms, at scale. Within the next decade, floating wind turbines could play a central role in the global clean energy strategy. Multi-gigawatt farms, massive projects, like the proposed ScotWind leases or Japan's Goto Island testbed, will deploy hundreds of floating turbines, targeting gigawatt-scale output. Modular designs and robotic installation are expected to drive rapid deployment. Hydrogen production at sea. Excess electricity from floating turbines could be used to power offshore electrolysis, producing green hydrogen directly on floating platforms. This sidesteps transmission limits and turns wind into an energy export product. Hybrid energy islands. Developers are envisioning energy islands that combine floating wind, solar panels, wave energy converters, and battery storage into off-grid power stations. These could power remote communities, offshore rigs, or serve as grid-stabilizing hubs. Final thoughts. Anchored in innovation. Floating wind turbines are more than clever engineering. They represent a paradigm shift. By turning oceans into power plants, we unlock clean energy on a truly global scale, beyond the limits of geography or land availability. Though early-stage challenges remain, the direction is clear. As technology matures, costs fall, and policy aligns, floating wind may become a cornerstone of decarbonization, especially for coastal nations with deep waters and dense populations. The next time you look out across the ocean, imagine not just waves, but silent giants harvesting wind, powering cities, and reshaping the future. If you enjoyed what you saw, don't forget to hit the like button and ring the notification bell so you never miss our upcoming videos. Your support means a lot to us. Take care until the next one, and feel free to drop a comment sharing your thoughts. See you soon.